We're at the Kimberlina solar thermal plant north of Bakersfield, California. I'm with Bill Conlon, who's the Vice President of Engineering for Areva Solar. Bill, thanks very much for inviting us to come out and take a look at the Kimberlina 5-megawatt plant. Tell us what we're going to take a look at this morning.
Well, sure, Dave. Thanks a lot. This is a CLFR, stands for Compact Linear Fresnel Reflector Steam Generator. So we use the sunlight that reflects off these mirrors here up onto boiler tubes that are elevated about 55 feet in the air. And so this is an ASME Section 1 boiler.
This is 25 megawatt thermal, 5 megawatt energy, correct?
This is in the overall plant, that's correct.
Overall plant,
This system that we're looking at, that we're standing in front of, is one of the modules, and a CLFR SSG, or solar steam generator, in this case is about a nominal rating of about 7.5 megawatts thermal.
And Bill, behind you is the balance of plant also that we'll be able to take a look at.
That's right. So this facility delivers steam to a steam turbine located in a building down to our right. But in addition, it's a development facility for Areva Solar, and it allows us to deliver steam either to the turbine or to a condenser. So we have a balance of plant system, a dump condenser that allows us to run experiments for customers at customer steam conditions to prove the operation, the stability, the transient behavior of the system at a whole range of conditions.
And it's still relatively early in the morning, and you're bringing the system up to operate it during the day.
So we typically model that the plant is able to start producing useful energy at about 14 degrees above the horizon, just about an hour after sunrise. This system starts up very quickly and is able to deliver superheated steam shortly after that, and then continues to run. We typically find that we can run this plant until close to sundown. In the roughly 2 years or so since we began construction here, 2.5 years since we began construction at Kimberlina, we built first 3 steam generators as saturated steam systems, a recirculating saturated steam system, very conventional approach. And in response to a variety of needs in the market, the need to deliver superheated steam equivalent to what the parabolic trough competitors do and so forth, we've evolved this technology to what we have today, which is a once-through steam generator. We bring feed water in and at pressure, and it comes out superheated steam. Today we'll be running at about 400 C, roughly 750 F. Leaving this steam generator. This is a Class 900 system designed for 1520 PSI, and it's delivering at 400 C today. But this was a system that we designed with some headroom, and its maximum allowable working temperature is actually 900 F. And we are just completing our trials at 750 F and are about to embark on the next step, which is to take it up toward 900.
Terrific. Well, let's go take a look. And what we're looking at here, this is the latest
right.
generation.
What we're looking at, we're walking alongside Steam Generator 4, SSG4.
SSG4.
And you can see that what we call the receiver is the boiler. And that's the elevated sections up there that are supported on the A-frame towers. One of the things I think a lot of people would find interesting is the way we build this boiler. So those A-frame towers are erected, and the boiler tubes are welded out on the ground. And in fact, we hydro-tested on the ground, okay? And then in a single coordinated lift, we take 1,200 feet of boiler off chain falls, supported off the A-frame towers, and we hoist that up. Wow. That's a one-day operation. But what it means is that all of the really expensive work is done on the ground. This system is a 2-pass, once-through boiler. So the feed water comes in, flows down to the end, turns around in a header, and comes all the way back. When you look at the systems next door, you'll see that they were originally designed, and you can't see it, but there is a pipeline down there that carries the recirculating water. Okay, that's the feed water that goes in the other 3 steam generators. So instead of having 1,200 feet of piping that we have to build on the ground, we carry it up in the receiver, and it's heated along the way. So this is not only a performance improvement, but it's a substantial cost savings. So each of these reflectors are ganged together in what we call a segment. And so there are 3 reflectors driven from this drive on my right and 3 reflectors to my left that are driven off this single drive. And this is designed to provide sufficient torque so that in a 40-mile-per-hour wind, which is our maximum operating wind speed, that we can safely stow these reflectors. Now that's another advantage that we have. As you can see that there's a galvanized steel backing on here, and we're able to rotate these reflectors face down. So in the event of a hailstorm, for example, these are protected, and we've done tests against that. We typically wash with a water truck, and we do what we call a deluge spray, where there's a hose and it sprays up, and these reflectors are angled so that the water will sheet and run off and carry the dust down to the ground. And you can see, if you were to gaze across here, you see that each of these reflectors are at a slightly different angle. And that's the Fresnel aspect of the design. So multiple reflectors, slightly different angles, just like you would have in an old lighthouse.
The objective of the higher temperature is what?
There are higher efficiencies to be obtained at higher pressures and higher temperatures. And so what this steam generator allows us to do is to prove our ability to deliver those steam conditions, pressure and temperature and flow rates, and to show people that it is controllable within the kind of temperature band that you would want at a power block.